Okay. Quick.
So, welcome back to Ops Lecture 8 3/4. It's themed after Harry Potter, mainly because we originally had lectures 8 and 9. As many of you might know, I might have known if you looked at the master sheet ahead of time, but that has changed because of certain time requirements. So we kind of merged these two for a single lecture. It's gonna seem like a lot of content, but it's not. We've chunked it down a little bit for you guys. Okay. Yeah.
First half of it is like information. The second half of it is information for the next project.
Yes.
So keep that in mind.
But the information is going to be beneficial if you guys choose to do like that, or just notes to do logic like M16. All right, so here's some general reminders. Spring has sprung, so we have new lab hours. Please make sure to check the website, IEEE Burns website. This has even changed recently. We've all added a lab hour, so now we're all doing 4 lab hours. For me, I added to 10 a.m. on Monday too, so I'm here for these 2 blocks, and then Miriam's here for mainly all day Thursday and also on Monday. Please make sure that if you have any questions, concerns, especially with the upcoming project and later on the capstone, we're there then. We can always coordinate another time to be there. It's just a matter of like, this is your assured time that we will be there and we will be able to help you. Okay. Otherwise, you just have to coordinate with us. That's also totally fine. Also, we have new projects coming up this next quarter. Well, just 2 mainly. We have our Bluetooth, our processing IDE project, and we have the capstone. So I know all of you guys have been waiting to finally finish ops. Maybe you're like, please. I'm just kidding. You guys love ops. No, but we are going to get into that after our last lecture, and also new officers. We're not gonna try and single any of you out, but remember that exec and admin elections are coming up these next 2 weeks. Exec elections are on Monday.
Be there.
Be there.
I'm gonna be there.
Yeah,
so you
I'm
should
gonna be there too. So you better be there. It's actually really important. Your vote is important. It decides the future of this club, especially for executive board. This is where you elect your president, your VP, your EVPs. People are going to run idea hacks. So these are the people that are going to represent you, not just in IEEE, but to the entire department. All right. So it's very important that you show up. At least you get a listen in. It's totally fine if you don't show up for the whole thing. Cynthia mentioned that you can show up for like half of it. And like help like the few that you were there for. But your vote counts and your vote matters. Also, if you're interested in being a project lead, like many of you are definitely interested in being an ops lead in the future, right? Please make sure that you submit your applications. I believe it's posted, like the links are posted in the main announcements channel. So please click on that if you plan to be a project lead. Also, if you plan on being well, you can't be exec, but plan on being an admin as well. Okay. So make sure you fill those out before the deadlines. There are no extensions on these, so that's something we can grant. But also we're super hyped to see like who does apply to be an ops lead. And also if you have any questions about being an ops lead, please ask us. And we'll be happy to help you at any time. And then also everything's still in the master sheet. Check that. We've updated a little bit of a lot of information, especially like all of our dates and times. Only one of the items on there is probably going to change, and that's the location of Capstone Work Session 2. You don't have to worry about that. That's like 7, so that's like nowhere near future. But if you guys want the most consistent updates on our schedule for ops, please reference that for the ops channel. We send out stuff there all the time. All right.
Okay. So, one announcement. This is also very. Oh, that's the wrong thing. This is also very far into the future. However, there is going to be a new project showcase event at the very end of the year. So if you have competed in a competition or competing in the Game Guido competition, wink, wink, nudge, nudge, we're going to be asking you to come to our project showcase and present your project and talk about it, talk about your experience in ops. Even if you're not one of these people who competed, you should still come. There's all the projects in IEEE are going to be there. And yes, there is food. And it'll be very fun and entertaining. Also, we've been plugging it a lot, but we are going to have ops shirts or hoodies. You decide. And this is going to be the design on the back of it. I made it.
Clap, clap, clap. That's a great
Thank you, thank you. But yeah, so just like fill out the form. It just asks which style you prefer and also what your shirt size is, because we need those in order to order the correct number.
Also, if you look at that cute design, it's literally all of the ops projects that we've done this year. You guys done it this year. This is our capstone too. So I thought it was really cool.
Yeah, each letter is a quarter, so
Yeah.
yeah.
Wait, really?
Yeah.
That's sick. I didn't even know that. That's sick. Okay. Wait, I didn't. I guess
Let
I
it
have no
sink
defense.
in.
Alright.
Yeah, I'm glad you like, but then you'll have it on your back if you fill out this form.
Fill out the form. Oh, also, in reference to that, please note that though the shirts are free, people who complete, well, first off, people who complete the capstone and most of the projects are going to be given priority. I feel like most of you don't have to worry about that. But just in general, for those listening to this recording as well, please note that you're still able to submit your late projects. If they're like late projects from spring, not spring, sorry, winter or fall, just DM us and we can check you off, open up the checkoff form again. Right now those forms are closed, but you just need to DM us. That's mainly so we can like remember to check it because it's so far in the past for us now. And yeah, okay. So just make sure if you wanna do the cool merch that's gonna drop. If you haven't like completed everything or you don't plan on completing the capstone, I don't know why I didn't, but in that case, please note that like you'll be like put on the tier like below the people who complete the capstone. Okay. It doesn't say you won't get it. It's just more like hierarchical. Yeah. Okay.
Yeah. Okay. So now we can get into the lecture.
All right. So I'm first going to cover reasoning and digital logic today, and then Miriam's going to cover binary and based numerical systems. After that, I'm going to cover some. Oh, actually, Miriam's going to take it on with UART and the HCO5, and then I'm going to cover processing IDE for you. And yeah, that's the basic structure of today's lecture. Ready?
Did it work? Okay, there you go.
So, like I said, I'm going to cover digital logic for you today. In this portion of the lecture, we're going to talk about Boolean algebra, logic gates, truth tables, and digital logic in real life. The MOSFET transistor, kind of a brief touch on that, and making gates, like how we actually implement these gates in real life, other than like coding, like something that you do in art. Okay. All right. So, kind of as a pre-intro. Here's this like cute little graphic I made in my free time. So you can tell there's a gym guy and a very nice woman. Together, they are going to talk about an intro to Boolean algebra. So we should go left.
Okay. I think right is a better option.
Nah.
Well, then choose one or the other. These animations take so long.
Yo, let it go. So now, as you can see, the gym man takes the road on the left, right? Okay. It's kind of slow. I'm sorry.
Wow.
Comedic effect. All right.
Road 1 or road 2. If you take any road, that means you made one choice. Wow, that's crazy. We call actions like this logic. Okay.
As you can see, I took the wrong road. So Miriam was right. So I'm probably gone, but it's okay.
Oh well. So you just keep screaming? Okay.
Alright, okay. Alright, so
that was
that's
beautiful.
The funny intro to logic. logic is something that defines all of our lives today, right? So you make a choice or another choice. You can make two choices at once. Unlike ourselves, we want to implement that into hardware and devices that we use, right? So we want to be able to make choices online, digitally, even with your computer, binary, all that stuff. Here's some example logic gates up here, the AND, the NOT, and the OR gates. They all have different functionality. For an AND gate, it works similar to like if you have, let's say you're trying to make a sandwich, right? Most of you don't want a sandwich with just bread. You want a sandwich with bread and something else, right? So to make a full, complete sandwich, which is what we would consider our output, we would need to implement both whatever else we're adding to the sandwich plus the bread, correct? All right. Meanwhile, you can think of like an OR gate, kind of like you're making soup, you know? Like if you want soup, you can have soup just alone, or you can have ramen, right? But either way, if you add ramen to it, it's still soup. It's just with ramen, right? So you can have it the way you like here. The truth tables work like this with an OR gate. It will return true regardless of what it will return true so long as both inputs are not false. And with an AND gate, it will only return true if both inputs are true. All right. And then a NOT gate kind of works basically just like the word not. You know, it's the opposite of what you put into it. It just inverts it. Now, okay. So I have a question for anyone. So what would 0 and 1 be? Someone raise your hand. 0. Correct. And then what about 0 or 1? 1. Okay. Oh, you read. Okay. Okay. That's just the basics of this. There's a lot more other types of gates. There's an exclusive OR gate, which works just like an OR, except for when both inputs are 1, it returns false as well. Okay. There's also a NAND gate. It's basically a NOT and an AND gate combined. We'll move into the next slide. All right, so here's a somewhat complex, no, not really complex, but complex digital logic diagram. Actually, I can't really show it here, but don't click, but
Okay.
can someone identify what type of gate this is? Ignore the little like. Not OR. Correct. All right, what about with this?
Oh, I was gonna guess not OR.
Yeah, correct. So it's a NOR gate. Good intuition. As for this, you said it's an OR, correct? This is an AND. So we have inputs A, B, C, and D, okay? Now, if we have inputs A and B, and we put them into an OR, right? The operation that's going to evolve is A plus B, okay? So when we do an OR gate, it's kind of like you add the bits, okay? And because it's a NOT, the line goes over the top. So whatever the OR operation is between the two, it's going to invert, okay? Now, for the following, we have C NOT right here. Can you click me? Sorry. C NOT will evolve out of here, and then what will come out of this OR gate? Someone who hasn't raised their hand. What?
C plus D?
Huh?
Which be C plus D?
Correct. And now, if I put, no, this is kind of just like a 3-pronged AND gate. What will happen if we put all of these into an AND gate? Does anyone know? It's okay if you don't know, because I didn't really cover it yet. No? Okay, so if an OR gate is addition, what would you think an AND gate is? Any ideas? Just pump it.
So if you think of it, it's like OR is like if only one of them is 1, then when you like combine them together, it still ends up with 1. So you can think of it as like 1 plus 0 will still be 1.
Correct.
Exactly.
So with an AND gate, it's multiplication, and as you can see here, we just multiply all of them together. Right? And as Miriam was saying earlier, think about it like the OR gate makes more sense if you add them together. So if you have 1 plus 0, it's still 1, right? True plus false is still true, right? False plus true is still true. True plus true is still true, but false plus false is false, right? In addition with AND, you have like true times false, that will always be false. You know, like 1 times 0 will always be 0. Okay. Does anyone have any questions with that? Yes, no? new stuff. All right. Now, this is kind of callback to transistors. We touched over that in which lecture? I believe it was lecture. Was it the last one or the one before? One of the last two lectures. We covered transistors, right? And three major types of transistors which we saw were PMOS, NMOS, and CMOS. Okay. Now, with a PMOS transistor, the input, when the input is 0, the output is a closed circuit. Okay. And when the input is 1, the output is an open circuit. And NMOS is the reverse of this. So it's kind of like the inverted version of PMOS, all right? Now with a CMOS, we can actually do some interesting things because it's a combination of both the NMOS and the PMOS. We can close the gates or open the gates inverting, well, one inverted from the other, okay? And transistors are operated based on their doping levels, okay? And because of that, they have different ranges, and usually when we refer to our transistor logic, and we use transistors in common applications, we use low or high. And what would be more familiar to you guys would be like our the 3 volts, right, versus our 0 volts, our ground. Okay. Now if we go to the next slide, I can actually kind of deep dive into the CMOS stuff. So now this is actually how we make a logic gate in real life. We use the transistors, the PMOS and the NMOS, to generate what's called like a CMOS gate. All right. Now this bubble, notation-wise, implies a PMOS transistor. All right. Now we have a PMOS transistor and a CMOS transistor in parallel to each other, and then on series with ground, we have two PMOS transistors in parallel with each other, and the series connection to ground, the NMOS transistor. Now, it would be weird. Well, actually, it's kind of weird to tell you this, but this is actually an AND gate in common hardware application, right? And the reason for that is, let's say we supply our VDD with a high voltage, right? So we know that with PMOS, sorry, this is in my mind. Does anyone remember what a PMOS transistor does at a high voltage? At what? Yes, no? Correct. So it does a closed circuit. So when we do that, both of these will close, right? And these will open. So our output will be high. Okay? In addition to this, we know that these right here, when they're connected to ground, right? That both are going to be low. That also means closed. So then we're going to have a 1. So that's where the actually. Oh, sorry, this is an AND gate. My bad. This will be low. My bad. And that's simply because this will pull it low, and our output will read low because current, right? So because current always takes the half of least resistance, in this case, it's going to read whatever's lower. All right. So when this is 1, on both ends, we're going to read a 0. Okay. So that's kind of a little base deep into kind of how this is made in real life. What you only need to know, really, if you use a logic gate, you'll be given the IC. You just need to know how that operates. You'll probably need to look at the data sheet to see operating regions. Let's say you're using AC source, right? In that case, like some sort of source of power. You would want to ensure that the functionality of the transistor, or your IC in this case, operates in the regions which you want for your application, okay? For the most part, we treat ICs, right, like a black box. So you just need to know the truth table that's associated with your logic gates. But kind of how transistors are actually applied in the real world, this is one application of it, okay? Other than digital switches, because I know we talked about that. Does this make sense for the most part? Anyone confused? It's okay to have a question. No? Okay.
Okay.
And I believe now it's Miriam's turn.
Now it is my turn to talk about binary and other bases. So I'm sure most of you have probably already heard about binary, and now we're going to kind of learn about like the intricacies of it and how to use it, and also bitwise operators, which are kind of complicated, but we'll just briefly touch on it at the very end. So first things first, we should probably figure out what a based numeral system is. It's well, 3 words, many letters, but it's really not that big of a deal because we use one all the time, and it's the decimal system. So every numeral system has a base, of course. The one that we use most commonly is the base 10 numeral system, which we call decimal. The base basically just determines at what point the number and the symbols begin repeating again. So like as we know, it goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we stick a 1 at the front, and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then so on and so forth. So when we reach a value of 10, we increment the next place value, and then we reset the ones place, and then we can continue counting up. So the four most commonly used bases that you're probably going to be seeing a lot more of as you continue into EE is binary, of course, octal, which is base 8, decimal, the one we always use, and hexadecimal, which is base 16. Octal is probably like the rarest. Like you don't really see that often anymore, but it's still something that's useful to know, and it's related. Okay, so also something very helpful is converting between bases because, of course, our brains, are wired to think in decimal just because we've been doing that our whole lives. So if we can convert, and that makes things a lot more easy. Main thing to keep in mind is just that, just for helping you think about how these different bases work. The ones place, of course, is the number of ones that you have. The next place is going to be you multiply that by the base that you have. So if we are in a decimal system, if we have a 1 here, and a 0 here, we multiply this by 10, so we get the value of 10, right? But if we were in binary, for example, and we had a 1 here and a 0 here, it looks like 10, but actually this is 1 times 2 plus 0, so it's actually a value of just 2. And then, of course, the next place would be we square the base. So if we had 1, 1, 0, then that would be 100 plus 10. But if we were in binary, then and we had 1, 1, 0, it would be 4 plus 2. So that's kind of the easiest way to kind of think about it. I have a couple of examples here. So converting to decimal, if we have binary, and I have the number 101, multiply 1 by 1, 0 by 2, 1 by 4, and we get 5 in decimal. Octal, if you recall, octal is base 8. So the ones place is still ones, but then the next place is going to be 8, and then the next place after that is going to be 8 squared, which is 64. So if we have 413, then we multiply the 4 by 64, the 1 by 8, and the 3 by 1, and we get 267 in decimal. Finally, we have hexadecimal. Hexadecimal is kind of weird because it uses letters, and sometimes we forget what the letters mean, or at least I do. But C, if you look at the chart over there, is 12. So if we have 2C0 in hexadecimal, multiply the 0 by 1, because that's in ones place, the 12 by 12, which is C, by 16, and then 16 squared is 256, so we multiply the 2 by 256, and we get 704 in decimal. So that's the conversion to decimal. And then we can also go backwards. Backwards is actually surprisingly kind of not that bad, because there's this really handy trick, which is using binary. So if we convert to and from binary, then we can just group things together, and we can. So the reason why we use octal and hex is because it's really easy to convert from binary. Is the point I'm trying to make. Sorry. So if we have a binary number like this, it looks kind of ugly, but if we just group it into threes, if we group it into fours, then we can convert it to hexadecimal pretty easily. Because if you recall, 2 to the 4 is 16. So if we just group this, this has a value of 16, so we can just turn that into a hexadecimal number. And same thing over here for octal, we can just group it into groups of 3, because 2 to the power of 3 is 8, and these each turn into a digit of octal. So yeah, pretty handy trick. Okay, so now the question is, why do I care? All these weird number things, why can't we just use decimal? Well, inside of a computer, as you may be aware, because you've done stuff with Arduino, a lot of things are in just ones and zeros. So you guys, you write pi, conmode, input, output, all that kinds of things. Those are all just ones and zeros, really. They can be represented as ones and zeros. And we need to be able to be familiar with this so we can ensure data accuracy and lessen the impact of noise. And the computer can also use a lot of much faster digital logic for powerful computation if we just stay with the most fundamental binary representation. So then the question comes, where do octal and hexadecimal come from? And the answer is, well, we need to know how to use binary. And because of all the reasons I stated before, however, binary is really ugly to look at. So we created hexadecimal and octal in order to simplify things. Would you rather write like 8 ones or just write FF? That's really like what it comes down to. And if you could count how many ones in that number, that'd be very impressive. But most people can't. Easier to just say 2Fs. Since it's easy to convert from octal to hex and binary, which is what we just looked at, that's the reason why they're commonly used in computer applications. Why it's helpful for you to know them too. Okay. Another thing that's kind of helpful to know sometimes is negatives. So negatives are kind of hard to represent because, well, how do you put a negative sign in binary? And the answer turns out to be this process called 2's complement. So you might have heard of like unsigned and signed. So unsigned basically means like all of the bits just refer to some kind of plain value that has to be positive. If it is signed, then that means we're using the first bit in our value to actually represent whether it is positive or negative. So if the unsigned range of a bit is 2 to the power of 32, or more than a bit, that's several bits, 32 bits in fact, then the sign range is going to be, because we remove what is that noise?
Hello.
Nathan, you scared me. Oh, hi. Okay. We've been interrupted, but it's okay. We'll continue. Okay, so if the sign range is from 0 to 2 to the power 32, because we turned that one bit in the front to represent the negative, now we can only go up to half of like the original value, but it can still represent the same number of numbers because half of them are positive and half of them are negative. So here's a couple of examples of how 2's complement works. Basically, you just make the, so you're still like multiplying it by like the value of that place, but it's -1. So then when you add it all together, it turns into a negative number. That's basically the idea. So pretty interesting. Okay, I'm not going to spend too much time on this, but if you want to know how to do math with binary, if you like pain and suffering, then feel free to look at this slide longer. Okay, we can continue. All right, this is the most interesting part, although also kind of most difficult to understand. So sometimes when we're programming computers, we want to be able, once again, to speak in their language. So if we want to check or change a single bit in a sequence of, like, say you have like this really long sequence of binary, and you only want to know what this one bit means, because this like one bit in this giant register is what represents like whether you're reading high or low or something. Then it's really important to be able to know how to check that or how to set that. So the way we do that is by using these bitwise operators. You've probably seen them before, namely as like or and or not. However, when you just put one of them, it becomes a bitwise operator. And this is how we use them. So this is like a table. If we have A is 0 and 1 and B is 1s and 0s, then this is what happens. You're basically just like oring and anding or nodding the single bit. So that's just how it looks like. How you would actually use it are over there. So setting is basically you want to make one bit 1. You use OR for that. So let's say I want to set this bit in the middle to 1. Then I would OR 0, 1, 0 with the value that I have, and voila, it becomes 1, 0, 1, 1, 1 because I set the 0 in here to be 1. If I want to clear it, which is the opposite, making it 0, then I'm going to do the AND bitwise operator with the not of the bit that I want to clear. So let's say I have 100, I want to clear that first bit, so I say AND not with 100, so that it gets ANDed, and then now I have all 0s. If I want to check a single bit, then I can just AND the value with the bit that I want to check. So let's say I want to check and see if the last bit is set high, and I see that, oh, my last bit ends up being 0 when I AND it, that means it's false. And finally, if we want to check that it's cleared, then I and them, but then I not it, kind of like the opposite of this basically, and it returns true in this case because I've knotted it basically. It's the same process as that. So yeah, it's actually pretty interesting when you get down to it, but a little bit difficult to wrap your mind around sometimes. Any questions on this slide in particular, or any of the previous slides? Great. Okay, I'm sorry, I know this has been a lot of content, but it just keeps going. So, now we're going to get into the material that you actually need to know for our next project, which is going to be the wireless flashlight. In particular, we're going to be using UART with the HC05, which is the Bluetooth module. So kind of an important review, and then we'll talk about the HC05 in particular. Okay, so this is basically just a copy of the communication slide that we had last lecture. So this is just revisiting UART. If you want to look at the UART function library, which you will actually now be using, there's a link there. Recall that UART is one-to-one, so the serial monitor is not going to work when you have your Arduino hooked up to the Bluetooth module, and also you're going to want to remember to like disconnect your UART pins because UART is how the Arduino gets programmed. So when it's getting programmed, you don't want to have those connected. It's also asynchronous communication. You need to make sure you have the same baud rate. There's start and stop bits, no clock. And the physical wiring, again, you're connecting the RX and the TX pins, and they need to have a common ground. Okay, that's just like fundamentals should be review. Okay, so here are some of the serial functions that we are now going to be using. Serial.begin, that one should be, pretty obvious. We've already used that one many times before. So that's just initializing the baud rate. Now we're also going to have serial.available. That's going to return a 1 if there is data available to be read. And you need to check that before you do serial.read, because if you don't have anything available and you read it, then it's probably just going to give you gibberish or freak out or do something else. Not good. Serial.read, of course, is going to read what's in the serial port, and then it'll return the first available incoming data, or it's going to return -1 if there's nothing available. And finally, we have serial.write, which is going to write a value to the TX pin, and it will return the number of bytes written. So those are all the important things you're going to be using. And next, I think we have example code of how you might use this. So we have a character called byte read, and that's a global variable to store the read byte. And setup, we are declaring our baud rate, starting our serial. And in the loop, you're checking if serial is available, and then when it is, you're going to read the serial and put that into byte read, and then you can also write out byte read back out to the serial port. So those are just like all kind of things that you could be doing using those functions. I don't think this is exactly the code that you will use in the project, but kind of shows you how it works. Okay, finally, this is the HC05 you've all been hearing about. So this is the Bluetooth module that we're going to be using. It's actually pretty cool because it's Bluetooth and you're like, wow, I didn't need to connect it and it works. But yeah, so we're only going to be using the middle 4 pins. Uses UART communication, which is why we've been reviewing it. So it sends and receives messages via Bluetooth. And as a result, it's going to require some setup, and there's probably going to be technical difficulties. So please come to the work session if you can. Also, it is not cheap. So please make sure you're not shorting out anything. And also, please consider that the Arduino TX pin is going to output 5 volts. And if that goes into this thing, this only takes 3.3 volts. You're going to need to make a voltage divider. Wow, crazy. You learned this, so you should probably be able to do it. Yeah, please use a voltage divider. It's important. If you don't, we will be sad because money. Okay. Okay. That's all I have.
Okay, right before I get into processing ID, I wanted to leave an edit on this slide. Sorry, I misread it. It's in regards to making the actual NAND gate in real life. Alright. So I'll create the work in about 15 Okay, so basically, I said, well, when I spoke, I referred to us changing VDD. That's incorrect. We are changing the voltage applied to the gates, or sorry, the base of your transistor. All right. In that case, it's like a little. Let's see if this actually has a You draw a transistor, right? Like a PMOS transistor here. This right here is our gate, okay? And that's what we apply. In the diagram, sorry, in the diagram we have this is A, and this is B. So when you apply a 0 and a 0 here, so it's low, so both of these gates, this becomes a short, and this becomes a short. So acts like a light in that case. And that's how we implement visual logic, okay? Sorry about that. And now I'm going to get into processing IDE. So what is processing? We're going to go over some functions, a little bit of drawing, and then we are again. There's also a really old meme in there. I'm sorry about that.
No, it's funny. I like it.
All right, ready? All right, so processing overview. It's an IDE made for programs with visuals. Oh, it was loud up there for a second. Yeah. All right. We can use it to make shapes, handle a calendar, and read and write bytes from and to serial ports. All right. And it's actually what we're going to be using for this project. Now, processing IDE is linked in the slides, which you'll get at the end of the lecture, or if you have signed in or have it on your laptop, you just click the link right there. It runs on a Java compiler, and we're actually going to do the project 6spec for the start code, kind of get you integrated into that. This is the what's the song?
What you meant in the summer
when the
heartbeat sound. We
I
found
thought
love
it was funny because people was
when the
airdropping
leaves
to
turn
me,
brown.
like everywhere. On the plane, I got that airdrop to me once, so it was a fun time.
We need
yeah,
audio.
This is just a logo for processing. So, all right.
Next.
All right, so some essential functions for processing IDE. It's kind of similar to your Arduino IDE in terms of like language ones. We have setup, and well, actually, it's just setup. In terms of the other functions we're using, it's draw, mouse click, and size. So in terms of setup, it runs just like the Arduino IDE. We use that to set our processing monitor and get running. For draw, it's also similar to the Arduino IDE's form of loop. Okay. In this case, it runs infinitely. So we put whatever we want to draw on the processing IDE in within the draw function. Okay. Additionally, we have mouse clicked and size. Mouse clicked only runs, guess what, when the mouse is clicked. Okay. And then size, it creates a window on a specific size. So imagine you want like 1040 by like 680 pixel grid or like some viewable screen. That's what it generates. Okay. We're going to use this to like kind of draw our own like digital screen and implement like buttons and functionality for functions. Okay. All right. Some other functions that we have are background, RGB. So remember how we dealt with RGB LEDs? Well, it's very similar with processing IDE, and actually with most digital logic. You'll see a lot of hexadecimal values when we deal with RGB. I don't know if you've ever like changed the color of your Bruin, like. You know, when you have the classes and you can change the color of your room light, those are usually hexadecimal. So it's like some X value and then there's a bunch of letters and numbers. That's how you can change your RGB colors on a rainbow scale. Okay. Similar to that.
Oh, sorry, my bad. Going back.
That's what the processing has. So we can set the background color using those RGB values. Okay, so red, green, blue. Additionally, there's fill. So in this case, we use this function to fill the color of shapes that we've made. And we can differentiate those based on the shape we have. So you can have like a triangle, like blue, or like a circle with pink. It's up to you. Right? Additionally, there's stroke. Stroke refers to the color around your shapes. Think about the lining. You know how sometimes in like Google Drive or like a table or something, you can implement the color of the grid around it, like the border. You can do something similar in Excel. You just can change the color of that. You can make it thicker, stuff like that. That's where stroke weight comes in. We can make the borders thicker. You can have like a pencil line versus like a very thick border so that they know what that Additionally, we have a text size function, which I'm gonna close this again. So, which sets the text size of our processing ID. In this case, it's like 12. It's like the normal point values that you use in like Google Docs, etc. And then we also have text. So within the text function, you can write a string, and then you can write the x and y coordinates. Obviously, there's no C because it is a 3D space. Your computer runs in a 2D string. So we want to make sure that we can write a text string at these specified coordinates. Unfortunately, there is no rotation, so you're gonna have to deal with straight lines. I'm sorry about that. But this will just point information. Okay. Now, for the Project 6 overview, we're going to be using the HC05, your processing IDE, and your Arduino IDE. All right. So with the HC05, we're going to program to communicate with your host device. In this case, it would be your laptop, most likely. Some of you that are running on like the whole like tablet laptop combo thing, like I think that'll work with there too. If you can run IDE, Arduino IDE on it, you can run all of this on it. Additionally, we're going to be using processing IDE, and with this, you're going to use 3 buttons to transmit process data, okay, across the what we call the buffer, which is the intermediate place in between your host device and the Arduino. Usually, it's in terms of with UART control, when we refer to it in the port, like the data that you get to process, it's called in the buffer. Okay, that's a terminology that you should be familiar with. Okay. Also, our code must send our Arduino must send and receive signals to operate an LED on your circuit. Okay. So basically, how this project's going to look is you're going to run code processing IDE on your laptop. You're going to click buttons on your laptop, and then your Arduino is not going to be connected to your laptop. It's going to change the LED, like turn it off, on, change the color, etc. So that's kind of cool, right? You can see life without wires. You can see life without connected devices. Well, technically they're connected, but physically connected devices, okay? All right. Oh, also, pitching time. We have workshops 3 this next Tuesday. We're going to be covering some of the stuff that we didn't really cover in terms of like fall quarter, just for light work. We're going to be covering PCB design. Well, that should be edited. The schematic design.
Okay.
And soldering. No, we're not going to teach you how to build a PCB. That's Micromouse stuff, but we will teach you how to scheme on Eagle, which, if you choose to be Micromouse, or even if you choose to apply to jump, scheming is a good skill to know. Okay. Additionally, we're going to teach you soldering. So for those of you that don't know how to solder, please come. This would be a great opportunity. You do need to know how to solder. I've had a lot of people ask me, Eli, how many times do you actually have to solder in the industry? It's good that you actually know how to solder. I actually haven't had to solder at any
I have. I have.
But Miriam has, right?
And I'm bad at it, so.
I will teach, Miriam and I will both teach you how to solder good. And then it's kind of fun. So the main point of it is to get you to scheme your own circuit and then build it on a per board that we have provided. A per board just is like kind of like a blank, yeah, a blank, so yeah, blank breadboard, so to speak. It's, for the ones that DigiKey gave us, it's a nice like that has copper on it, copper lining. It's literally just a breadboard, but like you solder onto it. Super nice. Usually, like some of the ones that we have in the lab are just plastic. It's a nightmare. Don't ever touch those. I mean, like ask the feelings to buy some more or something. I don't know. In terms of what we'll be doing though, you'll be scheming your own circuit, like your own circuit. We're just going to give you a prompt, and then it's all you. So this is very like intuition. If you want the engineering intuition, you want to deep dive into like making your own circuit. We're going to give you a problem. You're going to generate your own solution. You're going to scheme it, and then you're going to make it in real life. So that's what we're going to do in our workshop. Okay. And then.
Okay, I think this is another stroke of my graphical design genius.
Yes. So
it gets worse the more you look at it.
Project 6, the Bluetooth LED. You're a wizard, HCO5. So what we're going to do, with, like I said